Hello friends, this is the second lecture on solid state chemistry, and in this lecture I will cover imperfection of solids, magnetic property and electrical properties of solid. Now what is the imperfection? And I will go through point by point the defects. It is point defect and line defect, types of point defects, stoichiometry, non-stoichiometry, impurity, and the conductivity of the solids or imperfect solids, and magnetic property of the solids. Now, what is the imperfection? The imperfection in solids are any departure from the perfectly order arrangement of constituents particles in a crystal is called imperfect or defects. So what is this? Any departure from, that is A or A B B A B B A, this is the order structure. If any point is disturbed from its position or deviates or departure from the position, then the solid will be imperfect. Okay, and the defects are two types. First one is point defects and second one is line defects. So what is the point defects and why this defects is requirement, or why we will study these defects or imperfection of solids? Because to make or to get a perfect material or magnetic material or conductive material, okay, and superconductive material or semiconductive material, we need some imperfection in solid, because purely solid or purely crystal solid unable to conduct electricity through its electrons or by holes or by anions. Okay, so we need some imperfection. How? I will discuss it. So defects are of two types. One is point defects and another is line defects. What is point defects? The point defects are the irregularities or deviation from the ideal arrangement around a point or an atom in a crystalline solid. That's when if we consider this is a point, then if any point around this point or surroundings these points, if someone is missing or there are some irregularities, there is irregularities, A, B, in this way we can say it, A, if it is A, this B, A, B, A, okay, then A, B, B. Now, if anyone is missing or anyone disturbed from any points, then it will be a point defects. Let us consider if A is not there. What happened? There is no A. So this was the regular structure, but from here a point is missing. Or this point may comes here. Maybe, no problem. So any disturbance of the regular arrangement of atoms or molecules or ions is defects, and if it is disturbance from the points, then it is point defects. And line defects, what is the line defects? Line defects are the irregularities or deviation from the ideal arrangement in the entire rows, any rows, okay, from any rows one row, two row, or one row, two row. For irregularities of any rows means line defects. Now types of point defects: stoichiometry defect, non-stoichiometry defect, and impurity. What is stoichiometric defect? Stoichiometric defects are the point defects. What is this? Stoichiometric defects is the point defects. These are the point defects that do not disturb the stoichiometry. What happens? They do not disturb the stoichiometry. That means if it contains A, B, that's A, B, A, B, A, B, A, B, A, B. That's mean it contains 1, 2, 3, 4, 5, 20. Okay? There are 20 atoms is there. If one A and one B is missing, then ratio of the cation and anion are A and B, the ratio of A and B. Now here ratio of A and B equal to 1. Okay? If one A and one B is missing, then also the ratio remains 1. So there is no change of stoichiometry. Clear? Okay? If A and B both missing, then also stoichiometry is remains same. That means the ratio of A and B, number of atoms of A and number of atoms of B in the ratio is same. That means though the number decreases, from here A is missing, from here B is missing, the number of atom decreases, but their ratio is same. So stoichiometry is for the stoichiometry of this crystal remains same. If 1A from this point it missing and this A is found here, then again total number of A by total number of B remains same ratio. Okay? So this is the stoichiometry defect, and it is also known as thermodynamical defects. Okay? And these stoichiometric defects, in stoichiometric defects will get ionic solid and non-ionic solid. In ionic solid there are two types of defects. In ionic solid there are two types of defects, and in non-ionic defect ionic solid there are also two types of defects. At first we will take for ionic solid stoichiometric defects. Ionic stoichiometric defects. What is ionic stoichiometric defects? In ionic stoichiometric defects there are two types of defects. One is Schottky defects, another is Frenkel defect. What is this? Ionic solid solids. One is Schottky defects. What is this? Schottky defect. Clear? Schottky defects. And another is Frenkel. What is this? This is known as Frenkel defect. So one is Schottky defect, there is a double T. One is Schottky defects and another is Frenkel defect. In ionic solid, stoichiometric defects is two types. one is Schottky defects, another is Frenkel defect. Now what is the Schottky defects? Let us consider if it is A plus, okay, that is cation, anion, cation, this is polar plus, cation, anion in this way. Now A is cation, let's consider A is cation, B is anion, okay. We consider A is cation and B is anion. Then what is the Schottky defects? It always contains, for Schottky defects, equal number of cations and anions are missing. What is here? If one A is missing and one B is missing, then the stoichiometric ratio, that's mean A by B remains same before and after missing of cation and anion. So this type of defects, so this is a defect, it is a stoichiometric defect, and since the cation and anion both are missing, so equal number of cation and equal number of anions is missing from this regular structure. Hence this type of defects is known as Schottky defects. And what is the property of the Schottky defects? For the Schottky defects, since cation and anion both are missing, so this is empty, so density of the solid decreases. Yes. So what is the property? That's mean equal number of cations and anions are missing, and it decreases the density of the substances and is shown by the ionic substance in which the cation and anion are the almost similar size. So example, we can say KCl, the size of cation and anions almost same, okay. Sodium chloride, cesium chloride can shows this type of Schottky defects, though have the cation anion size is similar, okay. And what happened, like AgBr shows both Frenkel and Schottky defects. AgBr is a solid crystal which can shows Frenkel and as well as Schottky defects. So Schottky defect is when equal number of cation and anion is missing. But what is the Frenkel defect? What is the Frenkel defect? When a cation from anywhere is missing, but it takes an interstitial position in the crystal in the other side, okay. That's mean from here a cation is missing, but this cation present in the interstitial position. Interstitial position means in the middle position of cation and anion. So this point is missing, but this point is found in this interstitial position. So total number of cation and anion remains same. Clear? So again the ratio total number of A by total number of B equal to same, okay. So ratio does not change, hence this defect is known as stoichiometric defect. So for Frenkel defect, the smaller ion is dislocated from its normal sides to an interstitial site. Why this is the smallest ions? Because cation always smaller than anion, okay. Cation is always smaller than anion. And what is the other property? It does not change the density, okay. Because the total mass and total volume remains same. Since there is no missing of cation or anion completely, it just changes its position. Hence, the density does not change for Frenkel defect. Okay? Clear? And zinc sulfide, silver chloride, zinc sulfide, silver chloride, AgBr shows this type of Frenkel defect. And AgBr is a one solid structure which can shows Frenkel and Schottky defects simultaneously. Okay? Clear? So that was the Frenkel defect. Now, impurity defects. What is the impurity defects? Impurity defects, when foreign atoms are present at the lattice site in place of host atoms, okay, or a vacant interstitial position. That's when if a foreign atom, that's mean if A is missing from here, okay, A is missing from here, no problem. Then there is a one foreign atom. Let this is sodium, all are cation are sodium, anion are chloride. Then suddenly a SR2 plus takes the position of Na plus. Then what happened? That's mean one sodium cations replaced by SR2 plus ion. Then what happened? Then readily charge is unbalanced because there is a 1 plus. Now there is a 2 plus. So 2 sodium is missing. So it is a balanced. That's mean 2 cation, that's mean 2 Na plus is replaced by 1 SR2 plus. So this is the impure. Why it is impurity? Because there was a AA or Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. But replacing Na plus or 2 Na plus 1 SR2 plus is present here. So since SR2 plus is impurity here, this defect is known as impurity defects. Clear? So what is the impurity defects? Foreign atoms are present. Foreign atom means without Na plus Cl minus or A or B, there is another atoms which can replace 2 cations. That means 2 Na plus is replaced by SR2 plus by single atom. Okay. So foreign atoms are present at the lattice site in place of host atoms or at vacant interstitial sites. That's mean when SrCl2 is added to sodium chloride, 2 Na plus are replaced by 1 SR2 plus ion, producing 1 cation vacancy. So there is a cation vacancy. So for this reason, density must be changed because weight of the system will be changed. Okay. So for impurity defects, density must be changed. No problem. Now, what is the non-stoichiometric defects? What is the non-stoichiometric defects? The non-stoichiometric defects, when the ratio of the cations or anions becomes different. That's mean total number of cations are divided by total number of anions before defects and after defects is not same, the ratio is not same, then it is known as non-stoichiometric defects. That's mean if there is a 18 sodium divided by 18 chlorine, okay, ratio is 1, but 1 sodium is gone or 1 sodium is missing, then there will be 17 sodium but chlorine is remain same, then 17 divided by 18, so it is not 1, 18 by 18 equal to 1, but 17 by 18 is not 1, so this is not the stoichiometric defect, this is non-stoichiometric defect, okay. And it is look like it at that, this is actually, it may be metal excess, it may be metal excess or metal deficiency, okay. Metal excess, what is the metal excess? Due to anionic vacancies on heating, like sodium chloride, if it is sodium like Na plus Cl minus, 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 okay, Na Cl minus, Na Cl minus, Na Cl minus, Na Cl minus, Na Cl minus. Now what happened? Metal excess, what is meaning by metal excess? Let us consider this sodium chloride is heated in presence of sodium vapor, then what happened? Some anions leave lattice sites which are occupied by electron called F center. What happened? If sodium chloride structure is heated with sodium vapor, then if chlorine or chloride is leave the system, okay, if it is leaving the system, then what happened? And in the position of chloride, if there is only just one electron, that's means the charge is same. Instead of chloride ion, there is only one electron, so this is negative charge. Chloride means one negative charge, electron means one negative charge. Then we can see the number of sodium plus is higher than number of chloride minus. If there is a total 10 sodium plus, now there is 10 sodium plus and 9 chlorine minus, because one chloride minus is absent here. So it is actually non-stoichiometric defect, and since the number of cation is more than number of anion, number of cation is more than number of anion, hence this defect is known as metal excess defect, because number of sodium, if it is there 10, then number of chlorine is 9 and 1 is electron. So cation is excess here. For this reason, this is known as metal excess defect. Clear? So what is happened? And this site is known as F center. And what is the meaning of F center? F center means color, giving color. Okay. So due to the F center, the crystal is color. Okay. Crystal maybe change its color due to F center. Okay. Sodium chloride is white. Okay. But when it is metal excess, then it may be yellow. no problem. Now, due to presence of extra cation at interstitial site, on heating, white zinc oxide turns yellow as it loses oxygen and zinc 2 plus ions, and the electrons occupy the interstitial sites. If zinc oxide is, if it is zinc, it is oxide zinc, oxygen zinc, oxygen zinc, oxygen zinc, oxygen zinc, oxygen. Then if we heated the zinc oxide, then oxygen is removed and the position of the oxygen occupied by the electron. Then number of zinc will be higher than number of oxide ions. Hence, it will be also the metal excess defects. And this type of metal excess defects shows the yellow color. And what is the metal deficiency or metal deficiency defect? The metal deficiency defects usually occurs due to the missing of the cation from the lattice sites. Now, what was that? That was the missing of anion from the lattice site. If cation is missing, then the number of cation will be decreased and anion will be remain same. Then this type of defect is known as metal deficiency defect. Clear? Now, classification of solid on the basis of their conductivities. What is a conductor? Or metal is conductor or non-conductor, or the crystal solid is conductor or non-conductor? How we can determine the conductance of solid, or how we can decide a crystal solid will be conductive or non-conductive, or insulator, or it is semiconductive. Okay, that's mean the crystal may be subdivided in three types on the basis of conductivity. One is insulator, one is conductor, and one is semiconductor. Okay, so now you will go to for conductor or semiconductor and insulator, how we can define it. Okay, now let us consider a lithium. In lithium, there is a one electron in the outermost shell. So this is a one orbital and it contains one electron. Okay. Now, if two lithium, that's mean lithium one orbital, another lithium, there is another orbital. If energy profile diagram is here, then there is a one electron. This contains one electron. This means 2s orbital. Actually, this is 2s orbital. Okay. Now, after bonding, that's mean bonding orbital. This is bonding orbital and this is anti-bonding orbital. So there is a one electron, there is an electron. Then in the bonding condition, this electron, this two electron will be paired up and it will occupy the lower position of the bonding orbital. Okay, this is bonding orbital, this is anti-bonding orbital. So there is a two orbital in the molecular system. That's mean in Li2, there is a two orbital. One is bonding orbital, another is anti-bonding orbital. Okay, one is bonding orbital, another is anti-bonding orbital. So I am taking in this way. This is bonding orbital, this is anti-bonding orbital. Anti-bonding orbital is completely empty and this is the bonding orbital is completely filled up. Now, if another two lithium is coming here, then what happens? Then another bond will be formed and another anti-bond will be formed. Then again 6 lithium remains together, then 3 bonding orbital, 3 anti-bonding orbital, bonding orbital, anti-bonding orbital, bonding orbital, anti-bonding orbital, Okay. So when the bonding orbital and antibonding orbital, there is a energy gap. So this bonding orbital we can measure as like a band. Okay, this is a band. So this is a band. What is this? This is bonding orbital, whole bonding orbital, and this is known as valence band. Okay, this is actually, so this is a valence band. And what is this? This antibonding orbital totally is known as conduction band. So this band is here and this band is here. If the energy gap between valence band and conduction band is high, that's mean if one electron from valence band, if one electron can transfer to a conduction band, then if one electron is just jump to the conduction band, then electron will move from here to here. So there is a band, there is a huge conduction of electron. That's when electricity also. So if the energy gap between valence band and conduction band is very high, then electron will not transfer from the valence band to conduction band. So conductivity will not occur. Clear? Hence this system will be insulator. If the band gap, this is known as band gap. So band gap is high, electron will not transfer from valence band to conduction band, so conductivity will not arise. So this is known as insulator. If the conduction band and valence band, the gap between these two bands is medium, that's mean if you give some energy, then from the valence band electron can transfer to conduction band, then it will be semiconductor. And if two band is very close to each other, that's mean there is no gap between, or there is a very small gap between conduction band and valence band, then electron can readily move from valence band to conduction band and they can conduct electricity. So this is a pure conductor. So what is the difference between conductor and semiconductor? In conductor, the energy gap or band gap between valence band and conduction band is very low, and energy gap for valence band and conduction band is medium, that means semiconductor. When the band gap is high, that is insulator. Okay, in this way they are forming conductor, insulator and semiconductor. Clear? Is it clear? Now we can say conduction of electricity in metals in this way. Metallic conductors conduct electricity through movement of electrons in this way. Okay, and atomic orbital of metals, atoms form molecular orbitals like this. Lithium, there was a lithium, only lithium atom, then lithium 2, lithium 4, lithium 6, there is a overlapping orbitals. So the insulator, the band gap field valence band and conduction band is, the energy difference is very high for insulator. Okay, and there is a gap between valence band and conduction band. If we put some foreign element in some semiconductor, that's mean if we see that this silicon, if silicon silicon, 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 silicon. If there is a bonding in this way, I am taking silicon because silicon is a semiconductor. The band gap is intermediate of insulator and conductor. Now, if one silicon from here, if we remove, then one phosphorus is put here, then what happens? That's mean doping of foreign element to a semiconductor. What is this? Doping means, what is the doping? Doping, it is a process of adding an appropriate amount of suitable impurity to increase the conductivity of intrinsic semiconductor. Silicon was an intrinsic semiconductor. Now we are adding some impurity, okay, adding some appropriate impurity actually. Why it is appropriate? Because if phosphorus I am adding here, then we will see that in silicon there is a 4 electron in the outermost shell. 4, 4, 4, 4, 4, 4, 4. So 4 is silicon contains 4 electron in the outermost shell, but phosphorus contains 5 electron. So 4, 4, 4, 4, 4, 4, 4, 4, but it is 5. So there is electron excess. That's mean N-type semiconductor, that is negative charge is excess here. Then this negative charge, phosphorus will donate silicon, this silicon will donate to this silicon. In this way the negative charge will flow from here to here, here to here, here to here. Okay, in this way the conductivity of this intrinsic silicon substances, or the conductivity of the semiconductor, silicon semiconductor will increase. And since it is a negatively charged, that's mean negatively charged means the number of electron is higher than the 4 electron system. So this is a N-type semiconductor. If we dope boron here, what happens? If we dope boron, boron contains just 3 electrons in its outermost shell. Then 4, 4, 4, 4, 4, 4 electron, but here is a 3 electron. Then there is electron deficiency. That's mean hole. Hole means that is positive, or that's mean the deficiency of electron. Hence this 4 from this silicon, 1 electron will move here, then there will be a hole, that's mean 3 electron system. Then from here the electron will come here, then it will be 3 electron system. Then from here 1 electron come here, then it will be 3 electron system. In this way always a positive charge, that's mean a hole will move. Okay, that is from boron. This is a 3 electron system in its outermost shell. Then 1 electron will move here, then there will be a hole. Then from here 1 electron is moved towards this silicon, then there will be a hole. Then from here 1 electron will move here, then there will be a hole. In this way a holes will be moving towards the system, and it will be a positive or p-type semiconductor. That's mean if electron deficient system is a semiconductor, then it is a p-type semiconductor, because electron deficient or appropriate atom is doped here. Okay, now I will discuss about the magnetic property of solid. Magnetic property, that's mean classification of substances on the basis of magnetic properties. At first we will discuss in this way that paramagnetic substance, diamagnetic substance, ferimagnetic, ferromagnetic, antiferromagnetic. What is this? Paramagnetic. What is the paramagnetic? Paramagnetic substance is the substance are weakly attracted by a magnetic field. Paramagnetic means when a substance is weakly attracted by magnetic field, if there is electron, and paramagnetic substances contains unpaired electron, okay, must have an unpaired electron. Let us consider copper 2 plus. What will be the electronic configuration of copper 2 plus? That's mean D9, 4s2, 3d, or 4s1, 3d, 10. It was the actual electronic configuration, but when it is copper 2 plus, then it will be 4s0, 3d, 9. 9 means 1, 2, 3, 4, 5, 6, 7, 8, 9. There is one unpaired electron. So, for each cation, if there is a unpaired electron, then it will be paramagnetic and it is weakly attracted by the magnetic field. So, what is paramagnetic substance? The paramagnetic substance are weakly attracted by magnetic field. They have one or more unpaired electrons, that's mean, and lose their magnetism in the absence of magnetic field. Magnetic field যদি আমি রিমুভ করি তাহলেও কিন্তু আবার ম্যাগনেটিক প্রপার্টিটা লুজ হয়ে যাবে, থাকবে না। Then what is the diamagnetic substances? Diamagnetic substances, if substance contains paired electron and weakly repelled by magnetic field, what is this? It contains pair electron and weakly repelled by the magnetic field, which is known as diamagnetic substances, like sodium chloride or zero magnetic. It contains must contain zero magnetic moment because there is a pair of, that's mean overall magnetic, that's mean total spin is 0 because positive spin equal to half, negative spin equal to half, minus half actually, up spin positive half, down spin negative half, so addition is 0. So for all diamagnetic substances the magnetic moment will be 0 and it contains paired electron and it will weakly repelled by magnetic field, like sodium chloride. Sodium chloride is a diamagnetic substances, benzene is a diamagnetic substances, okay. Now ferromagnetic, what is ferromagnetic? What is ferromagnetic? Shows the substance shows the ferromagnetism, that's mean the substance will be ferromagnetic, those which shows permanent magnetism even in the absence of the magnetic field. It will shows magnetic property also. Iron, nickel, cobalt, gadolinium, etc. are ferromagnetic substances. That's mean it contains permanent magnetism even in the absence of magnetic field, okay. What is the antiferromagnetic? Antiferromagnetic substances are those which are expected to possess paramagnetism of the ferromagnetism or ferromagnetism, but actually have zero net magnetic moment due to the equal number of domains in opposite ions, okay, or opposite direction. That's mean if one electron is here, then one electron is here, one electron has here, one electron is here. That's mean in presence of magnetic field, some moment will be aligned towards the magnetic field and some will be opposite of the magnetic field. Then net magnetic moment will be zero. Okay, and what is the ferimagnetic substances? The ferimagnetic substances are those expected to have large magnetism but actually have small net magnetic moment due to the unequal number of domains in opposite direction. That's mean we can say there is a 1, 2, 3, 4, but sometimes this is, but overall magnetic moment is very low. That is positive, 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 negative, positive, negative. So there is a 2 negative, 5 positive. In this way, the overall magnetic moment will be very low. Clear? So in this way we can differentiate magnetic property. So this is very important part for your board exam. Thank you.